Section 4.1 is going to talk about probabilities. This is probably the section that drew me into this into statistics in the first place, is probabilities. Probabilities are going to be very tightly tied to statistics, and so it's important for us to understand some things about probabilities. The most basic one is this: probabilities are between 0 and 1, always. So what do those different probabilities mean? If you have a probability of a 1, that's going to mean that something will happen. It's guaranteed to happen. Ben Franklin has a famous quote about that. Two things that are guaranteed to happen: death and taxes. Probability 1. Can't get away with either of them. Now, on the other end, things that can't happen. All right? Now, I need a quick survey. Where are my Detroit Tiger fans? For you guys, how are you feeling about making the playoffs? Where should we put that probability right now? Higher or lower? Lower? Tell me when to stop. All right, Matt's not feeling very confident. So about right here? Okay. Yeah, all right. So not a high level of confidence from Matt. Anyone else feeling different? Nate, a little different? A little higher, we're going to make the playoffs?
Not too different.
Not too different? Okay, all right. So low confidence there. Now there's any degree of certainty in between, but the big thing is that probabilities are between 0 and 1. If you give me a probability outside of that, it's going to be very easy for me to grade, if you know what I mean. So now there's a couple ways you can determine probabilities. It depends on the situation. The classical approach is stuff that you would do like with dice. So you might recognize a couple dice from Dungeons and Dragons, that kind of thing. You could, for instance, say, all right, what's the probability of rolling an odd number? This is a 12-sided die, so that's a dodecahedron if you wanted to use the math term. It's got 6 even numbers and 6 odd numbers, so I could calculate the probability of rolling an odd number. It'd be 6 out of 12. Now, there's an assumption that you're making when you're doing that, and that is each of these possible simple events is equally likely. So that may or may not be true in certain circumstances. You have to be careful about using this approach. But that's the classical approach to probability. What's an example of a relativistic approach to probability? Well, that would be if you performed an experiment a lot of times and just counted up the relative frequency of how many times that your experiment or your event turned up. I did that with my morning class. I'm not sure we're going to take the time to do that today, although we can borrow the results. There's a web page, kind of a cool one. It's called random.org. And what you can do is click a button here, and it'll give you the coordinates of a random point on the surface of the Earth. Now, what we did this morning is I had my students click this a bunch of times and see how many times they landed in water. So my question to you is, what percentage of the Earth's surface is covered with water?
70-some.
70-some? Okay. All right. So here's what happened. I had all kinds of different groups of 2 people. They looked at how many times they landed in water out of how many trials, and our bottom line results were 260 times they landed in water with these random coordinates, 383 times. That was the number of trials, so about 68% here. So it's not too far off. That's actually something we'll return to later in this course, is an experiment about that stuff. But that would be a relative frequency approach to probabilities. You can do the same thing with getting struck by lightning. How many people live in a state? How many people got struck by lightning in that state? What state do you think it's most likely you get struck by lightning in? Any guesses? Seattle? Yeah. All right, let's maybe Washington. All right. But it actually turns out to be Florida. Florida is the state that you're most likely to get struck by lightning. So In any case, now there's one more probability that you can work with, and that's a subjective probability. And that would be something that you're just asking for somebody to give you a best estimate of what they think. So it could be the probability that somebody wins a game, or other events that people just kind of, it happens relatively speaking. They're doing these kinds of calculations in their head, and they give you a subjective probability. So 3 different ways that you can try and find these probabilities. There's some examples down here. We'll go over a couple of them, kind of on the quick side here. I want to spend some more time with some other things in this section. The relative frequency approach. When trying to determine the probability that an individual car crashes in a year, you examine past results to determine the number of cars in use in a year and the number of them that crashed. Then you can find the ratio, and that ratio for a recent year was a little bit under 0.05. So a little bit less than 5%. Does that mean it's likely that you're going to crash, or less likely? Yeah, it's kind of on the unlikely side, which is good. Which is definitely good. Classic approach to probability would be determining how many ways that something can happen, and then dividing by the total number of possible outcomes or total number of points in your sample space. When you're playing the Powerball, and I don't have the exact numbers, but I just know it's around 292 million different ways that you can select the numbers in the Powerball. And if you buy one ticket, that's your chance of winning. So, now, important detail here. This number is close to 0, but it's not 0. What would be the problem with the lottery if your probability of winning was 0?
No one would play.
Yeah, exactly. No one plays. Like, why do I want to waste money if I can't win? So the important thing is that it's not 0. Last but not least, subjective probability when trying to estimate the probability of getting stuck in an elevator, the next elevator that you ride. We know from personal experience that the probability is quite small. Let's say it to be 0.001, equivalent to 1 chance in 1,000. That's just somebody's guess. I don't know. Trying to think if I've ever been stuck in an elevator. Not really. I mean, it stopped here and there, but nothing that I would have felt stuck. So, did you? Okay. Yeah. Yeah, I mean, certainly I could understand something like that. Let's flip it over to the backside here. So go through for yourself and thanks, Oz.
Sorry.
Thank you, Oz. Appreciate you. Go through at the top here and decide which one of these are valid probabilities. So just circle the ones that are valid probabilities. I'm a little less than happy with this one, although I've seen this one in the text, so I left it here. We'll discuss that as we go through, but try and pick for yourself which one of these are valid probabilities. Some what? Jeopardy theme music would go good here.
You used to do that in college algebra.
Yeah.
When you used to do the pause.
Yeah, that was kind of fun. So what are we thinking here? How about a 0? Circle it or cross it off? Circle it 3/5. Circle it 5/3. That one's out. How about negative 0.25? 250%? What's the largest percent that we can use for a probability? 100%. You can't have anything that's more likely than 100%. 7 to 3, that's odds. We'll deal with odds later, but Is that a probability? No. Does 1 work for a probability? 50-50, I'm not really entirely happy with this one. Because on one hand, somebody could say, well, 50 minus 50 is 0. But what they really think that they're trying to kind of hint at is a 50-50 chance of something, coin toss, an even probability. But I don't like this one. So let's just give it, yeah, somebody said it for me, blah. I don't like that one. I wouldn't put that one on an exam. But the one next to it, 5-1. Yeah, that's again, those are odds. We'll deal with that towards the end of the section. And the last two, what do we got going there? Yes, and hasta la vista, baby. Nice. Now, a lot of times in working with probability, we'll use the proper notation, and that is, we're going to take a look at the probability in this one of a correct guess. So who discovered penicillin? Marcel Beech, William Penn, Johannes Salk, Alexander Fleming, or Louis Pasteur? Yay, Alexander Fleming. If you were to guess at that, what would be your probability of guessing correctly? If you're just going to pick a number or pick a name at random, what's your probability of guessing correctly? Yeah, 1 out of 5. Now, generally speaking, I prefer fractions for your answers and probabilities. You could also write it as 0.2. You could also write it as 20%. You know, if I don't specify something, you're free to use any of those forms. If I do specify a decimal, I'll probably tell you how many decimal digits I'd like. So do round your answer. We're okay with that one. Part of this is just to introduce this notation, probability notation, and probability, and then describe whatever event you're working with. Moving on down to example D. In a Pew Research Center survey, by the way, if you're seeing survey results from the Pew Research Center, they're a pretty reputable, research organization. I would tend to give their findings some good weight because they've been around for a long time. Randomly selected adults were asked if they have seen or been in the presence of a ghost. 366 respondents have said yes. 1,637 respondents answered no. Based on these results, find the probability that a randomly selected adult says that they have seen or been in the presence of a ghost. So let's again go at this with the proper notation. I'll look at the probability. I'm just going to call it ghost for my catch-all for having seen one or been in the presence of one. But you got to be a little bit careful with this one, because it's not just going to be 366 over 1637, is it? Why not? Remember, there's a lot of people in our survey, in fact, just over 2,000. So it's going to be the 366 over 366 plus our 1637. That's the total number of people in this survey. Be careful how they presented the results here. It was broken up into two pieces. Those that have not seen one and those who have. So a total of 366 over 2003. Nice. Nice. We're okay with that one. Thank you. Let's do another part of this problem. In a particular survey of internet users, 3,782 respondents say that they use social networking sites, and 1,373 respondents say they do not use social networking sites. What's the probability that a randomly selected person uses a social networking site? So I'm going to just go at it like this. Probability, social networking, probability of SN. Why don't you fill in the rest? If you're watching this later at home, then you can pause the action and give yourself a chance to answer it yourself. Let's do that.
Oh, we're recording. I know.
And he set down the recording, so you can keep that forever.
I know. He probably not gonna upload it this time.
No, no, probably not. So what should go in the numerator?
3782.
3782. Thanks. That sounds like Marvin. Thank you. 3782. What should I be writing in the denominator? You don't have to give me the total, but what should I be writing in the denominator? Nice. In the denominator, we want the total of those two things to get the total number of possible people in what's called the sample space. So it's going to be 3782 divided by 5,155. So the question is, to follow this up, do the results suggest that it is likely, that is with a 50% or greater probability, for someone to use social networking sites? Yes. Yeah. Although I'd be a little suspicious of this because they're polling internet users in the first place. So you're already using somebody, your sample is amongst people who are already at least a little tech savvy. But the answer to this second part here is yes. Yeah, I don't know the exact number. It's got to be bigger than 0.5, so yes. Comma, yes. Okay. Yes, please.
So we don't have to like look for the final answer in the just after like doing the 3782 divided by 51.
I'm typically not going to be looking for a decimal answer if that's what you're asking. This is fine. I'd be looking for both things here. I'd be looking for this as the answer to the probability, and then this for the answer to that last question, the one that I've highlighted here. So I'd want both things. Although I'm not sure I'm answering your question, so why don't you give me a follow-up?
Okay. Oh, I'm gonna just ask after class.
Oh, you can ask. Why don't you ask now? I mean, that way.
My answer is just way longer. I'm gonna just.
Okay. All right. Let's move down to example E. And for purposes of this problem, I'm going to assume that the likelihood of a boy or a girl at birth is the same. That's actually not true. I think boys are born slightly more frequently than girls. And of course, that's going to vary from country to country as well. But we want to identify something called the sample space. All right. So the sample space, that's like everything that can happen. That's all the little simple events that there could be. So let me start out by giving myself a generous amount of room. For the sample space. So sample space. We want to look at the sample space for the genders from 3 births. So we'll start out with girls first. If you're going to have 3 kids, you could start out with a girl, and then another girl, and then another girl. Or you could start out with a girl, and then a boy. Or we could flip it up, girl, boy, girl, and finally girl, boy, and boy. Now, in all of these cases, I've assumed that you had a girl first, and then I changed up these. If you play with these things often enough, you'll figure out the pattern here involved. Basically, I'm just kind of changing these things slowly, starting with the lower orders, moving up to the higher orders. But let's move over here. Now I'm going to start out with a boy in the first one. And the last one's going to alternate between girl and boy, girl and boy. So girl, boy, girl, boy. And then the middle one has to give me some variety as well. So I'll copy what I did here. Girl and girl, boy and boy. So that's all 8 things that can happen when you're looking at the genders from 3 births. We're going to look at 2 different probabilities. First things first, are you okay with the sample space here? Safe? Thumbs up, Angie? All right, thank you. So we'll do part A, probability of 2 girls. Now we're assuming that these are all equally likely events. In a lot of cases they might not be, that's all right. But here they are. So what should I put in the denominator? How many possible things are there in the denominator? 8. There's 8 events here. And if you're wondering about it, that's really 2 to the 3rd power. How many of them represent probability of getting exactly 2 girls? Well, there's 2 girls there, 2 girls there, and 2 girls there. Now we got to be careful. It said exactly 2, right? So can I count this event as being exactly 2? No. So how many different ways are there that this can happen? 3. 3 out of 8. What about part B here? Probability of at least 3, or at least 2, sorry. Probability at least 2. Does that change anything? Oz thinks it changes something. She's right. What does it change?
All units.
Nick?
The all units?
Yeah. We can now add in this one into our numerator, right? So you've got these 3 plus that one. Now there's 4 out of 8 is your chance of at least 2 girls. Now if you want to write it as 4 out of 8 or 1/2, doesn't matter to me. I'm just happy that you're getting the right fraction. All right. If you have it in lowest terms or not a big deal. Okay, let's keep on moving down with example E. Talk about some more notation. Are you okay with example, excuse me, I want to move to example F. Are we okay with example E there? Thumbs up on that one?
Question.
Yeah,
Why does
Christine?
the order of the births matter?
The order doesn't matter.
It's like we have 2, 'cause I mean,
I listed these, I was using kind of a system here to list them, but the order doesn't matter.
what's the
You could
difference
have,
between like girl, girl, boy and girl, boy, girl.
they're just different events. When you're having kids, you could be girl, boy, girl, or girl, girl, boy, or boy, girl, girl. Those are all the same event, or they're all the same kind of compound event of having 2 girls and 1 boy. So it doesn't matter where you're looking at in that order because you're just counting how many girls there were. So the order here is not really mattering. What matters is how many did you have. And that's where we got the 3 out of the 8. Does that answer your question? Is there something more about the order that's bothering you?
No, just that like that having a girl second instead of a boy second makes a difference. That it counts as
Well,
a that it
it's going to
counts
make
as
a
separate
difference in the
event, but you
family.
still have-
They are separate events. Yeah. Now our events, these are what are called simple events. You can break these down into bigger chunks if you wanted to. That's something we're going to do when we work with binomial probabilities. But for instance, you could just look at, the probability of the number of girls you know, 0 girl, 1, 2, or 3, these are no longer simple events. You're combining several things to get, for instance, you know, 2 girls. 2 girls is the combination of 3 simple events, these 3. Whereas, you know, no girls, that would be this event. That one's still a simple event because you can't break it down any further. But these, you know, probability of 2 girls, or the event of 2 girls, that is no longer a simple event. So we're just counting the simple events there. All right, let's move on to complements. And we're not talking about the compliment that you might say like, Oz, cool shirt you have on today. We're talking about a different kind of compliment, and that's going to be, well, let me demonstrate it this way by drawing a sample space to begin with. So this is example F. So what's the sample space? That's like everything that can happen. So the set of all simple events is your sample space. And now inside your sample space, I could have, you know, some kind of event. We'll give it a Venn diagram look with an A. So that's event A. So event A. And now I'm going to have this thing, A bar. So, you know, this is called the complement of A. And that's basically everything except what's in A. So if A is the event of flipping a heads, A bar is the event of flipping a tails. If A is the event of rolling a 6, then A bar is the event of rolling something other than a 6. So you're one or the other. So your heads or tails, 6 or not a 6, you know, fill on all kinds of examples on down the line. But that leads us to a nice little, you know, statement involving probability. And that is this one. What's going to be the probability of A plus the probability of A bar? What's the probability that one of those happens if you add them up? Yeah, that's going to be a 1. The probability that you get ahead or don't get ahead, one of those is going to happen. So your probability is going to be 1. This is kind of an innocent looking statement. You might look at that and go, yeah, well, it's going to be heads or tails. But the nice thing that you get from that is you can rearrange it. We can rearrange it as a probability of A bar is 1 minus the probability of A. Or the other way around, probability of A is 1 minus the probability of A bar. And those are going to be very useful. A lot of times it's easier to calculate probabilities indirectly rather than directly. It is looking at the complement to find those. So I keep these things handy. You will use them. So with that notation then, let's take a look at example F. And let's see. A certain group of women have a 0.43 rate of red-green color blindness. So let me define some notation here for us. I'm just going to go to lowercase r, g, c, b is the event. A randomly selected woman from this group. I'm not going to write from this group. I want to keep your notes a little bit more compact. Randomly selected woman has red-green color blindness. Oops. red-green color blindness. What's this event? What's that one saying? RGCB bar. What is that representing? Yeah, thank you. It's just the complement of it. This is the event. A randomly selected woman does not have red-green color blindness. All right, I'm running out of room there, so I'm just going to breathe red-green color blindness. Now, it's helpful to recognize, this relationship, the complement relationship, because what you're being asked for in this problem is to find that probability. Find the probability of RGCB. Now, let me make it very clear here, bar. I want to find that probability that they don't have red-green color blindness. They did give you something at the start of this problem, and that is probability of RGCB was 0.43%. Give yourself a quick test. Write that percentage as a decimal. What would that percentage be as a decimal? Write it down for yourself first before I write it up here. What's that going to be as a percentage? Nice. 0.0043. When you remove the percent sign, you have to move the decimal 2 places to the left. So, is there a big chance that somebody has red-green color blindness amongst women in this group? No, pretty small. About 43 in 10,000. But that still doesn't answer this question. How am I going to calculate the probability of red-green or not having red-green color blindness? All right.
1 minus 0.0043.
Yeah. So you're going to use the complement. 1 minus 0.0043, which is going to be 0.9957. So a pretty good chance that they don't have RGCB. Thank you. Okay. Nice use of our complementation rule. Were you okay with that one? Let's flip things over to the other side, which talks about an interesting company. Say again? I can't hear you.
The blank sheet of paper with the.
What are you looking for?
The paper we're just on before we.
The notes on the blank sheet, can you put them back up?
Oh, these?
Yes.
The next one?
The other
Oh.
one,
Oh, this one.
yeah.
Yeah.
Sure, sure. So this this Microsort company actually does exist. The Microsort that's part of example G. They were doing clinical trials about I don't know, dozen or so years ago, and they were told to stop. Come on, wake up. Not again. They were told to stop, and I think they still are available, but not in the United States. But let's see what this is all about. So the gender selection microsort technique is designed to increase the likelihood that a baby will be a boy. At one point before clinical trials were discontinued, 291 births consisted of 239 baby boys and 52 baby girls. Based on these results, what's the probability of a boy born to a couple using Microsort's Y-sort method? They also have an X-sort method too. If you ladies are feeling left out, they do have an X-sort method. But let's see if we can't find that probability. Probability of a boy. Nate, what you thinking? Probability of a boy. Is that right? 239 over 291? Yeah, that sounded pretty good. 239 over 291. So what do you think? Did this method appear to work? That probability, in case you're interested, is about 0.82. So the chance of getting this by luck and the fact that the method didn't work would be astronomically low. It'd be really, really unlikely that you'd have this many boys amongst 291 babies if this method didn't work. So you'd have one of two conclusions to make. Either you saw something really unlikely, or the method actually does work. And later on, when we start working more with hypothesis testing and stuff like that, we're going to use that and say, well, you know, at some point we're going to cut it off and say it's too small of a chance. There's actually a significant event happening here, and this method does appear to work. For now, all we need to do is calculate that probability, and then we're golden. So let's move on down to example H. See a little bit of the author's sense of humor here. On their first date, Kelly asked Mike to guess the date of her birth, not including the year. What's the probability that Mike will guess correctly? So what do we got there for a correct guess? Yeah, 1 in 365. Would it be unlikely for him to guess correct on the first try? Yeah, absolutely. If you were Kelly and Mike did guess correctly on the first try, would you believe his claim that he made a lucky guess, or would you be convinced that he already knew when you were born? What would your thoughts be? Eileen? What are you thinking?
Me?
Yeah.
Oh.
Would you be convinced that he got lucky, or
Yeah, no, probably not.
stalker?
Yeah.
Yeah. All right. There's probably a good chance that he found out ahead of time. So now, last one that everyone can answer. If Kelly asked Mike to guess her age and Mike's guess is too high by 15 years, what's the probability of a second date? Let's make that, yeah. I'm thinking 0. I think that is not going to happen at all. So probably the second date under these circumstances would just not happen. Okay. Nice. Let's move down to odds. And talk about odds for a little bit. Or we can talk about odds for a little bit. I mean, they're about the same, right? Okay, all right. So we're going to look at a horse race. And the odds in favor of a certain horse finishing in second place are given to be 20 to 80. Let's understand these odds. Now, these are odds in favor. And because they're in favor, this first number is the number of ways the horse can finish in second place. The number of ways you can kind of win that bet. So, ways you can win. What do you think the 80 what do you think the 80 represents here? If the 20 is the ways you can win, what do the 80 represent? Yeah, ways you can lose. Ways you can lose. So according to these odds, how many different things can happen? How many different events are there in our sample space? 100. Thank you, Matt. So there's 100 different things that can happen. And we can use that to calculate some probabilities. So it says express the likelihood or express the indicated degree of likelihood as a probability between 0 and 1 inclusive. So we want to turn this example of odds into a probability. Probability of finishing second. Let's do that. Let's see. Probability of second place. Now there's a couple answers that you can give, but it's all going to start out with doing kind of what Matt did for us, and that is he's going to add those two numbers together in the denominator. 20 plus 80. That's the total number of things that can happen. You're getting that directly from the sum of these two numbers here. There's 80 things that can happen. 20 of them are good, 80 of them are bad, at least in the terms of winning this bet. Now, of these 100 things, 20 of them are good. That's the way that you can win this bet. So 20 over 100, or 0.2, or 20%. Nice. That's the probability that they finish second. There's two different ways you can calculate the probability that they don't finish second. Right, Al? What would be one of them? What's one way we could calculate the probability that they don't finish second? I'll tell you what, let me write it here too. We want to find the probability that they don't finish second. So this is the complement of this event. No, the denominator's not going to change in this one. Some help? Garrett? 90 over 100? 80 over 100?
Or 1 minus 0.2.
Nice. So two different methods here. Let's appreciate both of them. So one way is to say, all right, there's 80 ways that you could fail to come in second over the 20 plus 80 or 100 ways. So that's, 0.80, 80%. Or the other way you could think of this is the probability of not finishing second is 1 minus the probability of finishing second. So you could do 1 minus 0.2, and again, that gives you 0.8. So a couple different ways you can think on that one. Both of them give you the same result. So either one is good. Well, let's see if we can apply some of that and learn some more things as we talk about example J. Are we okay with these two examples here? Let's apply this to example J. Now, in this example, we're going to use a weird roulette wheel. Now, if you've ever played roulette, maybe gone to Vegas, you know a roulette wheel has 36 slots plus a 0 plus a double 0 for a total of 38. This one, just for sake of giving you a different kind of problem, has 28 slots. 26 of them are the numbers 1 through 26, and then you've got this 0 and double 0. Now, neither of these count as an even or odd number. So when I look for the probability of winning, if you bet that the outcome is an even number, I have to keep that in mind. Probability of an even number. And I'm going to use hashtag there for number, even though you guys regard that as something different. Well, how many even numbers are there going to be on this modified roulette wheel? Well, you can't, two of these numbers can't be counted as even or odd, so we'll take those out. So that leaves 26 of them, the numbers 1 through 26. But of the numbers 1 through 26, how many of those numbers are even? 13, right? Every other number is even, so it's going to be 13 even numbers. How about our denominator? MA, what am I going to put in our denominator? Well, there's 26 numbers plus the number 0 plus the number double 0. Both of those count. Yeah, so 28. So there's your probability of an even number coming up. All right, thank you. Let's look at the next thing down here. So this is example J. This is A, B. It says, what are the odds against winning? Now let's go back here for just a second and notice what that denominator represents. That was the number of ways you could win and the number of ways you fail to win. So if I could break up my number here in the denominator into those two kinds of numbers, well, then I'd be in good shape. So let's think about it. That 13 represents the ways you can win, right? Ways to win. That's the 13. What does that leave left for the ways to lose? Colin? 15, yeah. So just breaking it up into those two numbers. But now we got those two numbers, we can look at the odds. I think they want it against, right? Odds against winning. So the odds against they're going to be this. There's the ways to lose, colon, ways to win. That's going to be your probability there. So in our case, 15 to 13. Okay. Not bad. Not bad. Are we okay with the way I split that up down here? Because once you split that up, the rest of it's not too bad. You're just looking at the number of ways to lose versus the number of ways to win. We could do that as odds for winning. Odds for winning. So we'll kind of complete this a little bit. What are the odds for winning? Well, it's still the same two numbers, right? There are 13 ways to win, 15 ways to lose. So 13 to 15. let's move into something that every gambler is going to be interested in, and that's the payoff odds. The payoff odds. That's these odds down here. Payoff odds against event A is going to be your net profit compared to the amount that you bet. So how much did you bet? How much do you net? That's your odds against, and those are the payoff odds. So our payoff odds, payoff odds, odds against versus odds for, or excuse me, net profit versus net or amount bet. Now in a casino, a lot of times when you're playing a roulette, depending on where you're putting your bet, you know, red or black, even or odd, those are payoff odds of 1 to 1. So those are your payoff odds, 1 to 1. You can kind of treat this like an equation. And the reason I'd want to treat it as an equation, because I want to figure out, well, if that's the payoff odds, and I made an $18 bet, and I win, how much am I going to profit? How much am I going to net? So what if we take our 1:1 and just, like I said, treat it as if it was an equation. I'm going to multiply both sides by 18. If I do that, what will I get? 18 to 18. And that's telling me if I bet 18, that's going to be my profit. Net profit. Bet 18, win 18. They'll hand you $36 back, but only 18 of that is your profit. So that's the part that we're concerned about. Now, it was really handy here that this number was a 1. That way I could just multiply both sides of this by 18 and figure out, okay, if I bet 18, I win 18. So that's just something I'm kind of putting out there for the next part of this. Comments on this much of it? Doing okay there? Okay. Let's see. Let's move on down to the next part. How much profit should you make on that $18 bet if you could somehow convince a casino to change its payoff odds so that they are the same as the actual odds against winning? So the odds against winning, let's recall those, were 15 to 13. Those are the actual odds against winning. So odds against. So if you're playing at a place that gave you the true odds, that's what they should be paying you for this kind of a bet. Now, in reality, they're going to pay you probably like 1 to 1. But if you could get them to do this, how much should you win on an $18 bet? Well, for myself, my money, the easiest thing to do is kind of start by figuring out, well, what would it be like if I had a $1 bet here? And I want to make this a 1, just like we did with the last one. Or, well, we didn't have to do it, but it was already there. Once this was a 1, we could multiply by 18 and figure it out that we won $18. To make this a 1 here, what do you think I could do to both sides to make this a 1? Yeah, divide by 13. Now you can do that number on your calculator. You're going to get a little over $1 for your dollar bet. Let me just find out exactly what that number is. So 15 divided by 13, about 1.538. So 1.1538 for every dollar you bet. But I don't want to bet just $1. How much do I want to bet in this case? 18. So to finish this problem up, you can take that 1.1538 and multiply both sides by 18. 18 times that, it's going to give me an 18 here and a little bit over 20 for the other one. So I'll take that and hit times by 20. No, times by 18, I should say. Times by 18. Yeah, $20.77. Okay. There's what we end up with. So are they kind of cheating you by a fair amount? If they pay you off 18? Yeah, they're underpaying you by a good chunk. Let's find out how much. If you divide this by 18, well, I guess we're going to get back to where we started from, right? Basically, it's about a 15% discount on what you should be getting. So that's kind of a bummer. They're not paying you what you're worth. Now, this problem will stop right here with finding that payout, what you should be getting paid if you were to get paid the true odds. So this should be the payout if they were paying you the true odds. Nice. Nice. So, why do you suppose they don't pay you the true odds? Yeah, exactly right. So they can make money. They couldn't, afford to keep the lights on if they weren't paying out, or if they were paying out the true odds. All right, they just end up going broke. So no, you're not going to get the true odds. Now, the difference between what they do pay you and what they should pay you, or how much of an advantage the house has on you, and by the house I mean the casino or wherever you're gambling, that difference is called the vigorish, or simply the vig, if you want to be short. Now, I'm not going to give you a lesson on gambling, but I will make a few kind of quick remarks. First of all, if you are going to gamble, only gamble with money you can afford to lose, all right? Because if you stay there long enough, eventually you will lose. The odds are just against you. That's just it. But the other thing is take time to learn your games that you're playing. If you're playing certain bets in roulette, then the house's advantage on you is about 5.5%. So that means, after gambling for a while, if you're making 100 $1 bets, on average, you'll end up with about $94.50 in your pocket. But if you play craps, and if you take the time to learn the game of craps the right way, you can get that house's advantage on you to less than 0.5%. So it's a much smaller advantage on you, and you've got a better chance of getting lucky in the short term. In the long term, you're going to lose. So, don't go in there thinking you're going to stay there for hours and hours and keep winning. It's just not going to happen. But if you do gamble, try and learn a little bit about your games, because there are certain good bets and certain bad bets depending on where you're at. All right, one last example here. Example K. It's on the back side. Here we go. All right, so we've got a little panel here, some results from some drug tests. And let me kind of cordon this off a little bit. These are the actual results. Let's put in some sums in this little table here. So for instance, 42 in 2019 is 61. And then over here, I've got 46 for a total of 107 this way. Now, the nice thing is that these totals should match when I take a look at the marginal totals from across. So here I've got 56. And here I've got, wait a minute, 54. How about 54? Sorry. 54 and 53. So a nice little double check on your arithmetic that the marginal total should match. But we want to use this table to answer a few questions. For instance, what's the probability of a correct result? So let's take a look at that. Probability of a correct result. Well, let's start out this way. What's going to be in my denominator? 107. Yeah. There's 107 people in this table. We're drawing from that. Now the question that you're going to think about a little bit is how many of these are correct results? Bless you. So what do we got there? Derek, what are the correct results here? Which ones of these would be correct? If somebody uses drugs and they tested positive, is that a correct result? All right, so we got a yes there. If they test positive but don't use drugs, is that a correct result? No. How about if they use drugs and test negative? Is that a correct result? Not there. How about if they don't use drugs and test negative? That's another correct result. So how many correct results do I have? So you should get 76 over 107. I think that was about 71%. Oh, somebody tell me a decimal answer on that one. What's the probability of an incorrect result? There's a couple ways you can approach this. Maybe you can take a look back at what we did earlier. What's the probability of an incorrect result? Matt?
Would it be 31 over 107?
Nice. So in this case, we want to take these two over here. Those are going to be in our numerator, divided by that 107. So 19, is it 19? Yeah. 19 plus 12 divided by my 107 is my 31 over 107. And that's fine. Is there another way that we could have calculated that one? How about 1 minus the probability of a correct result? And I'm just going to abbreviate that CR. But we calculate the probability of a correct result. That's going to be 76 divided by 107. And if you're looking at that going, man, that's like arithmetic. I don't do arithmetic. That's fine. Hopefully you've got a graphing calculator. You can just take 1 minus 76 divided by 107. Now that's going to give you a decimal number, but then when you hit the math key and hit answer to fraction, there you go, 31 over 107. So not bad either way. Last comments on example K. All right, let's put this one to rest.